Hi, my name is Katarzyna Olejnik, also known as Kasia. I'm with Raytheon BBM, where I've worked for 3.5 years now, and I'm here presenting our work on the semantic processing pipeline, quantifying the network-wide impact of security tools. So this is joint work between Raytheon BBN and the Air Force Research Lab. So to give you some context, what is a security tool? So a security tool is an executable which can be configured in various ways and is then executed to achieve a goal. So these are typically tools which are used by system administrators to monitor and manage the networks under their care. For instance, some examples of security tools would be the Nmap tool and the Tshark tool, which is the command line version of the Wireshark packet capture tool. However, there are various sources of uncertainty which come into play with configuring these tools, executing them, and then measuring whether they actually had the effect that you wanted them to have. So these sources of uncertainty can include the network configuration, which may be fully or partially unknown. The tool may have non-deterministic effects, and the tool effect may be difficult to quantify quickly. So for instance, perhaps you could quantify the tool effect by analyzing log files from across the network, but that's too time-consuming to be useful. So we introduce the uncertainty handling workflow, which is shown in the figure on the right, which helps determine the level of uncertainty and quantifies the network-wide impact of security tools. So I want to highlight two things here. So it helps determine the level of uncertainty, and it quantifies the network-wide impact. So that means we're looking at the effect across the entire network as opposed to looking at the effect on one host. So these two things really make this approach unique. So how does it work? Let's take a look at this figure over on the right. So we have a security tool which we put into the experimentation framework. So by that, I mean we design an experiment in an experimentation framework which will let us evaluate how the tool behaves in a certain environment. And by experimentation framework, I basically mean a cyber test range, for instance, EmuLab, or the cyber quantification framework, which any sort of framework like that, which lets you set up a network of virtual machines or containers, and then lets you analyze the interactions between those hosts and between the tool and the hosts. So after you execute this experiment, you're going to get some output files coming out of there. So these are the raw observables in the figure. So these are either log files or configuration files or both. Those we input into the semantic processing pipeline, which then transforms these into RDF, looks for connections and correlations across the data, and then produces a connected RDF graph as output. Next, that goes into the quantification mechanism of the user's choice, which quantifies the level of uncertainty or probabilities associated with these metrics, some of which are shown in the scroll-like thing in the bottom right. So detectability, attribution, and collateral damage are 3 examples of metrics. So in this presentation and in the associated paper, we'll be focusing on the semantic processing pipeline component of this workflow. And of particular interest to this workshop is the connected graph that's produced as output of the semantic processing pipeline. So this graph can be, in addition to just being a useful graph to understand what happened in the experiment, it can be serialized to produce labeled data for use with machine learning mechanisms or other quantification mechanisms than the one that we've chosen to focus on in our implementation. So how does this thing actually work? So I will go over the flow from 1 to 7, and I'll pause to explain concepts that are new, or which we've defined for the semantic processing pipeline. So these output files from the experimentation framework show up, and we input those into the semantic processing pipeline. So we examine next, in step 2, the configuration. So we look at the file names and compare those to the lifter classes which we have. So a lifter is a component of the semantic processing pipeline which will take specifically formatted input files and transform those or lift those into triples, RDF triples. So for instance, we can have, as you can see in the picture, we can have an XML lifter, which is specialized for lifting XML files, and then we can have a log file lifter, which is specialized for lifting .log files, and so on. So these are totally independent of each other. There's no interaction between these, so this process can be parallelized. So that's what a lifter is. So we take the matching files in that we were given and pass those to the lifters via the file dispatch. So that will actually execute each lifter, and each lifter will examine the file that it was given and transform that into RDF triples and push those into the triple store. So next, at step 5, we take a look, once the lifting is all complete, we take a look at the plugins that we are going to execute. So a plugin operates on the output of a lifter or operates on the output of another plugin. So this is where the more complex processing starts to happen. So plugins are also, because plugins can operate on the output of another plugin, this means there's an ordering inherent to the execution of the plugins. So they must be executed in a specific order. So a plugin consists of the following 3 steps. So it starts with a select query. So this grabs triples that it's interested in processing. And then those triples come back from the triple store. And then it does the processing that it's responsible for. So each plugin is responsible for computing a specific new piece of information based on the information in the select query that it grabs from the triple store. And then once it computes this new piece of information, it issues a construct query to add additional triples back into the triple store. And then finally, the component which is overseeing all of this is the cyber impact ontology, which you see in the middle there. So this is the schema for the format of these triples that all of these lifters and all of these plugins must adhere to. So having that lets us have easier integration between the different lifters and the different plugins. If they all adhere to the same schema, it's easier to create additional plugins and have different components interact with each other. So moving on to how do we evaluate this semantic processing pipeline? What's the scenario we're looking at, and what does our data set look like? So let's take a look at the topology over on the right first. So we have this following scenario. So we have this network topology with 8 target machines, 1 intrusion detection system, so IDS, which is running Snort, and then we have a tool launch host, which is going to launch an Nmap scan. So that's our tool under consideration, Nmap. So the story behind this scenario is, let's say we have this network here, and some attacker has gained inside access to this network, is going to issue an Nmap scan and see how much they can learn about the network. So in addition to that, we also have on targets 6 through 8, we have a vulnerable service running. So this service is brittle, it's a legacy service, and it's prone to crashing when it receives unexpected input. So that will also add some interesting complexity to this scenario, as you'll see later. So we have 3 Nmap configurations, we have 3 defensive workflows, and so we execute each 3 times, so that gives us 27 runs total. So some more detail about what we actually compute in the semantic processing pipeline. So the end result of the semantic processing pipeline is this connected graph, and the main metrics that we compute are these 5 that are listed here. So I just want to make a clarification, or just make sure that it's clear. So in that diagram at the very start on slide 2, we were showing that the metrics come out of the quantification mechanism. So the quantification mechanism actually helps us estimate the uncertainty or the probability associated with each of these attributes, derived attributes. However, for each experiment run that we do, we compute the specific values of these. So for instance, if we have an experiment run, and in that experiment run, the Nmap scan took, for instance, for the speed derived attribute, let's say it took 3 seconds, so then that's a data point that we have. But then once we combine all of those experiment runs together, we feed those into the quantification mechanism, at that point we get these probability estimates of how likely is it that, given this configuration of Nmap, that speed is going to fall into one of these buckets or brackets, so between so many and so many seconds, for instance. So these are the final derived attributes or metrics that we compute, and these are based on other intermediate metrics which are also computed by the pipeline. So success you can see is based on the percentage of IPs, ports, OS names, OS versions, etc. So in addition to having a value for success, we also have a value for percentage of IPs, percentage of ports, etc. And then that gets rolled up into the success derived attribute. We have the detectability derived attribute, so that consists of the following 3 components, which are listed on the slide. So that's based on whether the IDS, so in this case Snort, was able to detect that the Nmap scan was occurring, and whether it was correctly able to identify the type of scan. For instance, for example, instead of simply saying, hey, I detected a port scan, it's going to say, oh, I detected an Nmap scan. Collateral damage measures whether any of those vulnerable services crashed and did not restart. Speed is how long the scan took, and then attribution is whether the attack can be attributed back to an entity. So by that, we mean an entity like a person or an organization in the physical world, not just an IP address. So for the current scenario which we are evaluating, that's going to be very simple. So there's no obfuscation happening between the attacker, which is launching the scan, and the attacker is not making any attempts to obfuscate their identity. So in our case, for the Nmap scenario, this is going to be a very simple computation. However, we think that this may be important going forward. So we'd like to define the framework for computing this attribution still, even though that for the Nmap scenario is going to be quite simple. So here are all of the plugins that we've implemented in Java for our semantic processing pipeline implementation. So I'm not going to go over each individual one and what it does, but just notice that some of these plugins, their names are in italics. So that means that these are tool agnostic. So they can be used for the Nmap tool or any other similar tool. whereas the ones which are not in italics are Nmap specific. And so just connecting this back to the previous slide, so all of these plugins are going to compute the end result of the derived attributes, but they're also going to compute various intermediate features, perhaps you could say, as well. So that may also be useful. So, okay, so let's take a look at some of these results that we have. So this plot shows the runtime of each individual plugin. So this is across those 27 runs that we put together. So we have this data set. We ran this through the semantic processing pipeline implementation. And here are the runtimes and their variances for the different plugins. So we can see that some of these plugins, the runtimes of some of these plugins are varying a lot. So for instance, take a look at roughly in the middle of the plot, there is this massive blue box plot. So that's IDS detectability or intrusion detectability. That's that plugin. So this guy is varying a lot in its runtime. And yeah, so for instance, if you compare that to required rules, that one's varying much less in its runtime from run to run. And then generally, the DSF4 plugins have a longer runtime. So those are the blue box plots near in like the top half of the plot. So now let's take a look at the derived attributes that we computed from our data. So on the left, we have the different Nmap configurations, and then on the top, we have the different defensive workflows. So just to remind you, workflow 1 is do nothing, basically. It's a no-op. Workflow 2 blocks the source IP. Workflow 3 blocks the source IP and starts a watchdog for that vulnerable service. So basically, that's going to restart the service if it crashes. So we can see here in this top row, we can see that the more complex Nmap scan is unsuccessful. So the Nmap configuration 3, so the TCP SYN scan, is not actually able to succeed. So basically, it does not find a certain percentage of the operating system names, the operating system versions, and the different ports that exist in the topology. We can also see that the same Nmap scan, so this same Nmap configuration, generates an Nmap-specific detection event. So by that we mean that the IDS, so in this case, snort, is able to name specifically, hey, I am seeing an Nmap scan going on, rather than just saying, oh, I see some kind of port scan. And then finally, we can see that workflow 3 actually prevents collateral damage. So if we compare these boxes in the green with the other boxes, so not the top one, but perhaps the ones on the left, we can see that workflow 3 actually is preventing collateral damage by helping to restart this vulnerable service. So we also did a scalability experiment to see how well the semantic processing pipeline will scale. So we expanded our topology from 10 hosts all the way to 200. And then we ran these experiments and collected the data, ran it through the semantic processing pipeline using the same configuration as before. And we can see here that the overall trend is unfortunately quadratic. However, we suspect this could be due to complex Sparkle queries in some of the plugins. And I'd like to make a note that the overall runtime is low, so even for a 200 host topology, it takes roughly 1 minute for the semantic processing pipeline to extract that connected graph. And then over on the right, we can see that most of the time is spent either executing plugins or executing lifters, so lifting the raw log files into RDF. So to conclude, one limitation that is clear is that extending this to other tools requires special expertise. However, as the plugin library grows, so meaning the plugins that are in existence, which were listed in that table a few slides back. So some of these are going to be some of these are going to be tool agnostic, meaning that as we extend to additional tools, it's going to be easier and easier to do that due to this reusability of some of these plugins. So for next steps, we'd like to adapt this to other tools. We'd like to introduce a plugin complexity metric to sort of estimate and figure out why some of these plugins are taking, why some of these runtimes vary so much for some of these plugins. Perhaps it's due to the plugin being too complex, trying to do too many things. Excuse me. And then finally, we'd like to also optimize the Sparkle queries associated with some of the plugins to make them more efficient. All right, that's all I've got, and thanks for listening, and I will take your questions now.